The Infinite Monkey Theorem states that a monkey hitting keys at random on a typewriter keyboard for an infinite amount of time will almost surely type any given text, such as the complete works of William Shakespeare. In fact, the monkey would almost surely type every possible finite text an infinite number of times. However, the probability that monkeys filling the observable universe would type a complete work, such as Shakespeare's Hamlet, is so tiny that the chance of it occurring during a period of time hundreds of thousands of orders of magnitude longer than the age of the universe is extremely low, but technically not zero. In this context, almost surely is a mathematical term with precise meaning, and the monkey is not an actual monkey, but a metaphor for an abstract device that produces an endless random sequence of letters and symbols. One of the earliest instances of the use of the monkey metaphor is that of French mathematician Emile Borel in 1913, but the first instance may have been earlier. Variants of the theorem include multiple and even infinitely many typists, and the target text varies between an entire library and a single sentence. George Louis Borges, I don't know how to say his name, traced the history of this idea from Aristotle's On Generation and Corruption and Cicero's De Natura Deorum, also known as On the Nature of the Gods, through Blaise Pascal and Jonathan Swift, up to modern statements with their iconic simians and typewriters. In the early 20th century, Borel and Arthur Eddington used the theorem to illustrate the time scales implicit in the Foundation's statistical mechanics. Direct proof. There is a straightforward proof of this theorem. As an introduction, recall that if two events are statistically independent, then the probability of both happening equals the product of probabilities of each one happening independently. For example, if the chance of rain on Moscow on a particular day in the future is 0.4, and the chance of an earthquake in San Francisco in any particular day is 0.00003, then the chance of both happening on the same day is 0.4 times 0.03 equals 0.00012, assuming that they're both indeed independent. Suppose a typewriter has 50 keys, and the word to be typed is banana. If the keys are pressed randomly and independently, it means that each key has an equal chance of being pressed. Then the chance of the first letter being typed as B is 1 out of 50. And the chance that the second letter typed is A is also 150. And so on. Therefore, the chance of the first 6 letters typing banana is 150 or whatever. 1 out of 50 times 6, which would be 625 million. Less than 1 in 15 billion, but not 0. From the above, the chance of not typing banana in a given block of 6 letters is 1. I'm not saying that, because each block is typed independently. The chance of X tiny n of not typing banana in any of the first n blocks of letters is X little n whatever, and these things are in parentheses. 1 subtract 1 over 56, so whatever. As n grows, xn gets smaller, for not an n of a million, for an n of a million, actually. Xn is roughly 0.9, but for... I'm not going to read that. The same argument shows why at least one infinitely many monkeys produce the text as quickly as it would be produced by a perfectly accurate human typist, copying it from the original. In this case, xn equals 1 subtract 150 with tiny 6 in parentheses on top and where x whatever represents the probability that none of the first n monkeys types banana correctly on their first try. When we consider 100 billion monkeys, the probability falls to 0.17%. And as the number of monkeys n increases, the value of xn negative the probability the monkey is found to reproduce the given text approaches 0 arbitrarily closely. The limit for n going to infinity is 0. So the probability of the word banana appearing at some point in an infinite sequence of keystrokes is equal to 1. However, the physically meaningful numbers of monkeys typing for physically meaningful lengths of time. The results are reversed. If there are as many monkeys as there are atoms in the observable universe, typing extremely fast for trillions of times the life of the universe, the probability of the monkeys replicating even a single page of Shakespeare is unfathomably small. Ignoring punctuation, spacing, and capitalization, a monkey typing letters uniformly at random has a chance of 1 in 26 correctly typing the first letter of Hamlet. If it has a chance of 1 in 676, or 26 by 26, typing the first two letters, because the probability shrinks exponentially, at 20 letters, it already has a chance of being 1 in 26 20ths. In the case of the entire text of Hamlet, the probabilities are so vanishingly small as to be inconceivable. The text of Hamlet contains approximately 130,000 letters. Thus, there is a probability of 1 in 3.4 times 10 183 946 hundredths, I believe, to get the next right at the first trial. The average number of letters that needs to be typed until the text appears is also 3.4, whatever thing I said last time, or including punctuation. I'm not going to say it. I hate that. Even if every proton in the observable universe were a monkey with a typewriter, typing from the Big Bang until the end of the universe, when protons might no longer exist, they still would need a far greater amount of time, more than 360,000 orders of magnitude longer, to have 1 in 10,500. That's wild. Of success, chance of success. To put it another way, for 1 in a trillion chance of success, there would need to be 641,000 observable universes made of protonic monkeys, as Kittel and Kromer put it in the textbook of thermodynamics. The